How information rides the waves. What do surfing, lasers, computer circuits, televisions, rock concerts, and the ever-popular death ray have in common? They all depend on waves. Without all the types of waves that surround us and that penetrate us at all times, and without the ability of waves to carry information nearly instantly to all parts of the globe, chances are civilizations we bask in it today would have never have happened. It takes no great technology to use waves to send information. You simply turn a wave on and off. It's the basis for jungle drums, Morse code, the earliest modems, and it's called encoding. Regardless of the form of encoding, the sound or electrical waves are not changed. Information is encoded in how often a wave is created and how long the wave exists. Morse code and the first 300 baud modems use short and long pulses of electricity to create a simple binary code, a forerunner of how data is stored and transmitted to computers. The short dits and the long das in different combinations represent different letters of the alphabet. A total of 9 pulses of electricity are enough to code the 3 letters that represent SOS, the Morse code distress cry. Note that the frequency and amplitude of the electrical signal does not change, only how long the same electromagnetic signal is broadcast. Here's a high level of noise when the key is pressed, dit dit dit, da da da, dit dit dit. Little or no signal when the key is not pressed. Long and short drum beats are not possible with jungle drums. They depend on recognizable patterns in which volume of individual beats and this length of silences between the beats create a pattern that can convey information. Because we're not fluent in jungle drums, here's a visualization of a 22-second drum solo by 𝗔𝗂𝗃𝗧𝗏. The breaks in the waveform depict bass drum beats. At the right end of the segment, you can see how intervals between the bass grow shorter and shorter, creating the type of pattern we could, if we didn't have all our phones coming out of our ears, use for communications. Amplitude modulation makes changes to the amplitude of a wave. Frequency makes change to the frequency. Jungle drums and Morse code have obvious limitations. Both are slow and depend on a skilled person doing a hands-on job. What is needed are entirely different modulation methods. 3 modulations methods do the job. FM, frequency modulation, AM, amplitude modulation, and pulse modulation. Pulse modulation is the newest way to add information to waves and get information out of them. It was developed because modems had reached a limit as to how quickly and accurately they could turn a signal on and off. The solution was to use different frequencies or amplitudes to stand for combinations of letters. This scheme is an enormous improvement over early modems, but is limited to text and digital information. Transmitting analog signals without first converting them to digital signals requires AM or FM. Either AM or FM can be used to convey information over radio waves or electrical circuits, using frequencies from 100,000 Hz radio through microwave to 10,000 billion Hz infrared. The higher the frequency, the smaller the wavelength. Radio waves are about as long as your average skyscraper is tall. Microwaves are the length of an adult person, and infrared waves are the size of a computer mouse. Various factors govern a wavelength's usefulness for carrying data. Some radio waves penetrate brick and steel buildings. Others bounce off of them. Generally, the higher the frequency, the more data it can carry, because the more often a wave moves between peaks and valleys, the more opportunities there are for modulating it to carry information. Interesting. You always wonder how the radio works, right? To understand modulation, go to a pond or a lake and throw a rock in the water. If you throw only a single rock, it creates waves that expand in concentric circles, smoothly and evenly from the point of impact. We call this our carrier wave, and measure its wavelength, how quickly it expands, and how tall and deep its crest and trough. As the carrier wave expands, toss a few pebbles across the width of the carrier. The pebbles make waves of their own. The pebbles' waves change, as in modulate, the carrier wave whenever they meet. If we measured all the directions the combined waves move, their speed, and where they eventually meet the shore, and then, using some sort of math I don't even want to think about, we subtracted the influence of the carrier wave, we'd be left with the information we need to know, where each of the pebbles struck the water and the force behind each. A radio carrier signal, like the watery carrier wave, is a simple steady wave at a specific known wavelength, like 92.3 here in New York. We mix the carrier wave with a wave known as an input signal created by the sound or sights from another source. The two waves combine into a modulated signal that is then broadcast over the airwaves or through wires. When a radio, TV, or other device receives the modulated signal, it removes the influence of the original carrier wave. What remains is a replica of the input signal that created the modulation. How electromagnetism is the ghost in the machine. Just got a couple pages left, and then we can turn to something maybe a little more sophisticated, but I do like this. It's a lot easier to understand than the book on shift registers. How electromagnetism is the ghost in the machine. This book begins with a quote from Arthur C. Clarke, any sufficiently advanced technology is indistinguishable from magic. Well, we're still not past the first chapter, and it's already time to start the magic show. Like good magicians, electricity and magnetism, the twin powers of electromagnetism, hide what they're doing. They mostly show the results, the rabbit coming out of the hat, not how it got into the hat. We can see the effects of magnetism on iron filings, refrigerator doors, and the giant generators that supply much of our energy, but we cannot see magnetism itself. It's a silent partner in the electromagnetism spectrum. We can see electricity in the form of lightning and sparks from a shorting wall plug, and we can certainly feel electricity when static electricity jumps from our fingers on a cold day. Static electricity is a buildup of surplus electrons. Combined, magnetism and electricity form the electromagnetic spectrum, the full frequency range of the mysterious waves that permeate the universe. This partnership continues into other areas where these conjoined energy ghosts form the basis for the most modern of technology, for most of modern technology. Electricity and magnetism cannot survive without each other. The previous illustration shows that magnetism and electric fields cooperate in a bootstrapping operation that allows electromagnetic waves such as light, radio, and heat to travel through a vacuum. Let's start with the electro half of electromagnetism. In some atoms, such as copper and silver, the attraction is weak between the atom's core, a nucleus made of positively charged protons, and the negatively charged electron clouds in the atom's outer layers. In such conductive materials, it's possible for electrons to jump freely from one atom to another. This movement of electrons, which occurs only under the right circumstances, is electricity, and it travels at the same speed as light, another form of electromagnetism, which is 186,000 miles per second. All right, we apply three measurements when working with electricity: voltage, amperage, and resistance. It's convenient to think of voltage, or charge, as being like water pressure, how much power is behind electricity. Amperage, or amps, is the measure of how much electricity is flowing through the wires, similar to how much we measure gallons of waters that pass through pipes. And resistance is how the material through which the electricity is flowing. In these examples here, higher water pressure overcomes a clogged pipe, and doubling the voltage pushes the same amount of current despite the addition of a resistor. So here's a battery, the resistor I mentioned a while back on the cover. Both readings the same on an amp meter measuring voltage. In some materials, such as rubber and glass, electrons are more closely bound to their nuclei and do not easily move from one atom to another. These non-conductive materials are called insulators. Still, other materials like silicon can act as either conductors or insulators depending on the conditions. These are semiconductors, which are an important component of microchips and transistors. Lower pressure, less resistance with a clear pipe. Same amount of water gets through when you have higher pressure, and more resistance when the pipe is clogged. When electricity moves through a wire, it generates a magnetic field that surrounds the wire. The magnetic field is a straight piece of wire is too weak to pick up even the smallest iron filings. Conversely, when a wire moves through a magnetic field, the interaction creates an electric current in the wire. Note that in order for either of these phenomena to work, the wire must be moving through a magnetic field, or the magnetic field needs to be collapsing or expanding across the wire. Both magnetic fields caused by electricity moving through in a wire and electricity created from magnetism can be made more powerful if the wires are wrapped around iron cores. Almost all electricity we use comes from generators, in which massive magnets surround equally massive coils of wire. Water from a dam or steam created by a nuclear plant or fuel-burning plant spins the wire coil rapidly, creating a high-voltage alternating current that is transmitted via thick, low-resistance cables to electrical substations throughout urban areas. Interesting. How do we control electricity? Straight from the generators, electricity measures in the thousands of volts, much more powerful than we need for everyday uses. Even in the home, the voltage of current from a wall plug is many more times more than most household electronics need or can tolerate. Within those same electronics, different components require still smaller and varying voltages and amperages, higher or lower than the current flowing through most of the circuitry. How do we control all this? At a power station, steam generated from burning coal or heat from a nuclear plant turns a shaft within an electric dynamo. The shaft is attached to a rotor covered with thousands of wires called bushings. The rotor turns inside two permanent stator magnets whose fields generate high voltage electricity in the bushings that is transmitted as alternating current to the public power grid to homes and businesses. There's the stator magnet, the rotor, and the current comes out, I guess. There's the residential power transformer. Before the electricity reaches its final destinations, it passes through the transformer to reduce the voltage. Transformer has a common magnetic core, usually iron, around which two wires are wrapped. Alternating current, electricity that flows first in one direction and then another, moves through the primary coil, the wire that has more wrappings around the core. The transformer cannot use direct current, which flows only in one direction because the magnetic field cannot create electricity in wires unless either the wires or the field are moving. Interesting. Each time the current switches directions, its magnetic field expands or collapses, which is the same as the field moving, and induces electric current in the coil. The current passes through the part of the core which is wrapped with the secondary coil. There the AC produces another magnetic field that envelops the wire wrapped around the core. The field creates a current in the secondary coil, but because the secondary has fewer wrappings, the current created in the secondary coil has a smaller voltage, making this a step-down transformer. A step-down transformer, which is most likely mounted on a utility pole near your home, cuts the voltage of the raw generator current from thousands of volts to 120 volts before it's allowed inside. There's a step-up transformer and there's a step-down transformer. Before a computer can use the household current, the current passes through a second step-down transformer, this time in the PC's power supply, the box festooned with warnings not to open it, that's at the back of the computer. This transformer reduces the 120 volts current into two different voltages that separate wires carry to 5-volt and 3-volt components. Other electronic devices, such as amplifiers, use a step-up transformer to raise the same 120 volts to a level powerful enough to drive speakers. We use resistors to decrease the flow of electricity, much like we use a valve to limit how much water flows through a pipe. Resistors are commonly made of carbon, plastic doped with metals, and metals such as nickel chrome that do not conduct electricity well. Varying the materials and their size and shape changes how much resistance the component has, measured in ohms. Color coding tells how many ohms of resistance the part provides and the percentage by which the value may vary. I used to know how to read these. A spiral cut in the resistant material determines the resistance value. A narrower spiral increases the ohm value of the resistor because it creates a longer path the electricity must follow. Does anybody know the color coding of the resistors? Variable resistors, such as the rheostat, shown here, it's a great term, are used in situations that call for the resistance to be changed manually on the fly. The best example of a traditional dial controlling volume on a radio. The outer ring, or toroid coil, consists of a resistive wire wrapped in a spiral about a ring of insulating material. Cool. Maybe you'd have to make this yourself in a desert island, or a deserted island. Do you think you could do it? Electricity must travel along a sliding wiper and through the coil before it leaves the resistor. When the knob is turned clockwise, electricity has less wire to travel through so that the resulting current is stronger and the volume is louder. Capacitors, oh man, these are old friends of mine, are made of two conductive materials that sandwich a material with limited conductivity, such as plastic, ceramic, or even paper. When current is applied to the two conductive terminals, the electricity does not flow through the capacitor. Instead, electrons from the power source pile up at one end of the terminals called the anode, like logs swept on a dam. They leave a dearth of electrons on the second terminal, the cathode, so that it is charged positively by the protons that have been deserted by the electrons. The charges remain in the capacitor for a few seconds to several minutes, depending on the design. When a circuit connecting the two terminals closes, the capacitor discharges, the electrons jump the insulator, to send a bigger than usual burst of current needed for, say, a photoflash or something like that. Larger capacitors, such as those found in CRT monitors, cathode ray tube monitors, and some power supplies can be dangerous or fatal if handled improperly. So there's the kind of capacity building. How computers create our world using numbers. So this is sort of ties it all together. Waves, electromagnetic fields, particles, electrons, light waves, and quarks. These are the elements by which computers operate or compute, measuring, comparing, adding, and subtracting. All that computing brilliance has to be communicated to us less brilliant organic units in some way. Unfortunately, the native tongue of computers is numbers, which most of us stop thinking about within days of completing Algebra 2. Because we're not fluent enough in numbers to enter the world of computers, computers have devised ways of using numbers to recreate our world as we understand it. Their numerical constructs are so smooth that we're rarely aware that they are made of only ones and zeros. There are two ways to take stock of the world around us, analog and digital. An analog instrument expresses measurements in a manner that is analogous to whatever it's measuring. An old-fashioned thermometer is an analog device. It has a glass tube filled with red-dyed alcohol. As the thermometer gets warmer, the heat causes the alcohol to expand and rise within the tube. We can look at the markings along the tube and say that a person's temperature is about 99.5. We say about because a reading of the temperature depends on the precision used in making the thermometer and the acuity of our vision. A digital thermometer has an electrical component called a thermistor. Rising temperatures make the thermistor less resistant to electrical current, allowing an increased electrical flow to a mini processor that converts the amount of electricity to numbers that represent the temperature. The numbers are displayed on a screen, but unlike the alcohol in the analog thermometer, the numbers don't swell or shrink in proportion to temperature variations. Most of today's computers are digital because the transistors that jumble data are digital, either on or off, and not some state in between. Analog computers are used in situations involving constantly changing measurements, such as the automatic transmission or a bombardier's sight. Digital computers, however, often start off with analog measurements that must be converted to digital. A computer-based digital camera replaces film with an image sensor, a microchip studded with photodiodes, which are transistors melded with substances that convert photoenergy into electrical energy. Each of the photodiodes collects photons of light, building up electrical charges as long as the shutter is open. The brighter a part of a scene, the more photons are focused on pixels capturing that part of the scene. When the shutter closes, all of the pixels have electrical charges that are proportional to the number of photons that hit each photodiode. If you picture photons piling up in mounds of glowing pebbles in buckets, some larger or smaller, you have the idea. The camera circuitry moves the charges collected by the image sensor into a single row that passes through an amplifier. The amp converts what are little more than faint static charges into an electrical current with varying voltages in proportion to the parade of changing charges. The current passes into an analog to digital converter, ADC. Every few milliseconds, the ADC measures the voltage of the current as it passes through. If the voltage is above a certain level, the ADC produces a 1-bit, which it adds to a stream of digital values that it passes on to other components. If it's beneath a certain level, the ADC adds a 0-bit. That has only two values, 0, 1, doesn't have the versatility to represent in the analog format the real world of images and sounds that, ironically, have become the most popular use of computers. With only two values, such as black and white and no grays, an image looks like this 2-bit Mona Lisa. One can obtain more precise digital representations of analog signals through multi-bit sampling. The current being measured, whether generated by energy of light, sound, or chemical reactions, passes through a series of resistors. Each resistor depletes some of the current until it's no longer measurable. How many resistors it passes through determines a value, depending on the design that is represented by 2 bits, 4, or 8 bits, the bit rate. Diagram A on the far right, with a bit rate of 4, there are 4 values the voltage could reach for each sample. With diagram B on the right shows an ADC capable of registering 8 bits per reading. Diagram B also demonstrates how the conversion's resolution is made more accurate by increasing the sampling rate, the frequency at which samples of passing current are measured. In diagram A, 8 samples are taken for the period shown. Diagram B shows a sampling rate 4 times greater. If diagram A were representing the digitization of a music recording, its sampling or frequency rate might be appropriate for a smooth slide on a trombone. Diagram B has the same general shape as the red line in A, but the higher sampling rate provides opportunities to capture variations in sound that the first can't handle, for example, a rapid trill on a clarinet. Having 16 bits for each sample might not sound particularly useful, but 16 bits in a binary number yields 256 different combinations. In creating video color, that means 16 bits can produce any 256 shades of a color, as shown here with red. A bit value of all these zeros is this 16 zeros. Binary, or 0 and decimal, is assigned to total black. All ones, binary or 256 decimal, represents a pure and intense a red as a monitor can produce. Take any 2 adjacent red squares shown here, and the difference between them is less than the human eye can distinguish. combine 256 shades of red with 256 shades of the other two colors that go into a video image, green and blue, and the result is an amazing 16 million possible colors. An ADC is a functional mirror image in a DAC, or a digital to analog converter. Some monitors and most speakers require analog currents. The DAC changes a string of digital values into rapidly changing voltages in electrical current by routing a feeder current through a matrix of resistors that partially block the current. The resistors are weighted to represent different degrees of resistance. Sending current through resistors on different pathways turns out a final stream of current that corresponds to the digital data. That's how our speakers work. And that's chapter 1 of what makes a computer, or how does a computer work, how computers work, which is CS50 suggested reading in Harvard.